Morning. This is the second lecture on crystal structures. We'll follow this with a lecture on glass. Again, refractories, three major components in their microstructures: crystals, glass, and porosity. And they all affect the properties. So this course is followed by a course on microstructures. And then it's followed by a third course on property. So it ties together the crystal structures, glass, the microstructures, and the properties. So we'll finish up crystal structures this morning. We did single and binary structures last class, so we have to finish with some ternary element structures, the non-oxides, carbide, and silicon nitride. Also silicon carbide and silicon nitride type structures. Fire clay bricks, high aluminum bricks have clays as part of their raw material, so we'll go over clay minerals. And some of the refractory materials exhibit polymorphic phase transformations and also have different crystal defects. So we'll go over those for more background. So in a ternary structure, there's three distinct atom types. There's going to be two cations, one anion. And again, these are going to be close packed arrangements of the ions. And then the two different cations, different sizes and charges, are going to fit in the interstitial positions. So these are a list of the different ternary structures. The structure names, the general formulas, A, B, and X. This is AB2X4. It's a spinel, but A and B are the cations. X is the anion. So spinels are important in refractories. The inverse spinels are also important. Olivine structures like phosphorite, the magnesium silicate is important. Zircon, ZrSiO4 is important. Silica is a refractory material. Calcite, the carbonates of calcium and magnesium, those carbonates are basically a solid solution dolomite, and they're heat treated and produce the dolomite oxide type material. So we'll go over some of these different materials that are more important in refractories. So the first one is spinel, AB2X4. So the oxygen ions are in a face-centered cubic close packing structure. And then the subshell contains 4 oxygen ions that are cubic close packed, 4 octahedral sites, and 8 tetrahedral sites. So the large circles here are the oxygens. So they're at the corners of the cube, and then they're also at the face centers of the faces. So it's face-centered cubic. And then right in the center here is an octahedral site. So there's one atom above it, one below it, and then on the faces, there's 4 other atoms. So it's in an octahedral site surrounded by 6 oxygens. And then there's another tetrahedral site here. It's surrounded by these 4 oxygens. So the oxygen ions are in this face-centered cubic structure. And I just showed a subcell. It contains 4 oxygen ions, 4 octahedral sites, and 8 tetrahedral sites. So at the corners, there's 1/8 oxygen in this subshell. So there's 8 corners that contributes 1 oxygen. And then on the faces, there's a half of an oxygen in the subshell. So there's 6 of those, giving rise to 4 oxygens plus the corners. So there's 8 oxygens in this subshell. 4 octahedral sites and 8 tetrahedral sites. So there's 12 interstitial sites, and that's to be filled by the 3 cations, A and 1A and 2Bs. So there's one divalent A cation that's A plus 2, and then that goes in a tetrahedral site, and there's 2 trivalent cations, the B plus 3. They go on 2 octahedral sites. So we can put together 8 of these subcells to form a large unit cell. So the unit cell is going to contain, now instead of 4 oxygens, it's going to contain 32. Instead of 1 tetrahedral site, it's going to contain 8. So 32 oxygen ions, 8 tetrahedral divalent cations, A plus 2, and now 16 octahedral or trivalent B plus 3 cations. So A plus 2 ions are going to occupy 1/8 of the tetrahedral sites, and then the B plus 3 ions are going to occupy half of the octahedral sites. So this is the unit cell for spinel, AB2X4. X is the oxygens, the large open circles. The cations in the octahedral sites, the crosshatched circles, that's the B sites. And then the dotted circles are the cations, the A sites. So this is an octahedron with the cation, the crosshatched cation in that site. And that's shown right here. You can see the 6 oxygens surrounding the cation. And then this is the tetrahedral site. You can see one right here. There's 4 oxygens surrounding the cation. So there's 2 types of spinels. The normal spinel, we just described AB2O4. So the A plus 2 cations are in the tetrahedral sites. The B plus 3 cations are in the octahedral sites. So these are our different examples. The spinels that you would see in refractories are MgAl2O4. These are all spinel structures, but this mineral is actually called spinel. You might see some of other ones like MnAl2O4, FeAl2O4. Some of these may be present as impurities, or the chrome minerals have multiple types of spinels in them. But our synthetic spinel, that's a refractory material, is MgAl2O4, and it's a normal spinel. So there's normal spinels, and then there's inverse spinels. So the A and B cations are switched. So it's B on an A site and an A and a B on a B site, O4. So BaBO4. So A plus 2 cations and half of the B plus 3 cations are on the octahedral sites. That half of the B plus 3 cations are now on the tetrahedral sites. So that's known as an inverse spinel. So a spinel that you might see in a chrome mineral is FeMgFeO4. You can see that the Mg and the Fe is reversed here. Another spinel that you'll see in chrome minerals is Fe3O4. This is actually FeFeFeO4. So there's Fe plus 2 and Fe plus 3 ions in Fe3O4. So those are the 2 types of spinels. Olivine is another refractory material, A2BX4. And olivine is a magnesium silicate, Mg2SiO4, that's phosphorite. This is a refractory material by itself, but it's also a small phase, a small amount of phosphorite is in MgO type refractories. But natural olivine is actually a solid solution of phosphorite and phthalate. Phthalate has this A2BX4 structure. It actually forms a solid solution with the phosphorite. So it's MgFe2SiO4. The Fe ion is substituting for an Mg ion, so it's a solid solution. And solid solutions usually have ions of the same size and charge substituting for each other. The problem with olivine is that phosphorite's a high temperature material, phthalite's a very low temperature material. So the higher the phthalate content, the lower the use temperature of that particular olivine. So this is a close-packed hexagonal array of oxygen ions with half of the octahedral A+2 sites occupied with either magnesium or iron, and then 1/8 of the tetrahedral B+4 sites occupied by silicon. So this is the olivine structure. You can see these are the oxygens. They form a tetrahedron, and then you have two Mg+2 or Fe+2 cations that are balancing the charge of this SiO4 minus unit. So there's 4 oxygens here, and in the center of this tetrahedron is an Si ion, has a -4 charge, and then the cations Mg+2 and plus Fe+2 balance the charge. So this is a 3-dimensional structure. So you have a continuous placement of the Mg+2 and Fe+2. That would be at these sites M1 and M2. These cations are placed between the SiO4 units in 3 dimensions, and the charge balances. So these structures are getting more complex. So olivine, again, is A2BX4. For the oxides, phosphorite, Mg2SiO4 is an important refractory material. You'll also see phthalate, Fe2SiO4, the undesirable impurity, and then there's some other oxides here that I listed. Zircon, AbX4, an example is ZrSiO4. So this is in this AbX4 structure, and it's zircon, the zirconium silicate. It's a refractory material. So in this structure, you have parallel chains of alternating silica tetrahedra. So you have a silicon ion in 4-fold coordination with the oxygen ions. And then the zirconium octahedra, you have large zirconium ions in 8-fold coordination with the oxygen. So the structure looks something like this. You have silicon ions in 4-fold coordination with the oxygen ions. So this would be a silicon tetrahedron, a silicon in the center surrounded by 4 oxygens. And these are sharing face edges, sorry. And then zirconium ions are in 8-fold coordination. This is a zirconium ion. They're in 8-fold coordination with the oxygen ions. So you can see the hexagonal structure here, the arrangement of the zirconium ions. So again, zircon is AbX4. The refractory material is ZrSiO4 zircon. I've listed a couple other oxides, and then there's a fluoride here that's also in the AbX4 structure. I've listed a calcite, CaCO3, a calcium carbonate. That's the AbX3 structure. Calcium carbonate is the raw material for CaO, lime, which is a high temperature refractory material. CaO has the issue dealing with hydration, but it is a refractory material. And it's a component in dolomite, which has also has the magnesium carbonate. So you have a solid solution of calcium and magnesium carbonates in dolomite. You calcine them, you end up with CaO and MgO, the oxides. So calcite is this structure, AbX3. So you have large cations, the Ca+2 cations in the A position, and the small cations, carbon+4 in the B position. So each of the carbon+4 cations are surrounded by 3 oxygens in one plane. So that forms a triangle. Then each CO3 group has 6 Ca+3 neighbors. So it looks something like this. This is calcite. Here is a CO3 group. Carbon is in the center. Oxygen are at the corner. So they're forming triangles. And then here's your Ca+2 cation. It's surrounded, has six neighbors. So it's surrounded by these 6 oxygens. So that's calcite. So other oxides that have this structure, I mentioned magnesium carbonate, MgCO3, and again, calcite, CaCO3 and MgCO3 form the solid solution mineral dolomite. And then I've just listed other carbonates. There's some borates like FeBO3 and some nitrates like NaNO3. So these all have this calcite structure. And I think the last ternary structure I have here is AbX3. So the large cations, A+2, form a face-centered cubic structure with the anions, the X-2 anions. So the small cations, the B cations, the B+4, are sitting in the octahedral sites. This structure is a little more simpler than the previous couple. So perovskite is CaTiO3. Oxygen is the large open circles. Calcium, the shaded circles on the corners. Oxygen is on the face. And then Ti is in the center. So Ti+4 is in this octahedral site. It's surrounded by these 6 oxygens. And then Ca+2 and O-2, they both form a face-centered cubic structure. So Ti is in the center, and both oxygen and calcium are in a face-centered cubic structure. So there's various oxides that form the perovskite structure. Barium titanate, BaTiO3, is one. None of these are particularly important refractory materials, but I just wanted to include this ternary structure. Materials like barium titanate are actually electronic type materials. There's also some fluorides, which are in the perovskite structure. There's fluorine instead of oxygen in the X site. So we went over binary and ternary crystal structures. Also want to include carbide and nitride, especially silicon carbide and silicon nitride. So these are both silicon carbide and silicon nitride are high temperature refractory materials. They suffer from oxidation at high temperatures, so they have to be protected. So in silicon carbide, you have the large silicon ions. They form a close packed structure, and the small carbon C-4 ions are in interstitial positions. So it turns out that silicon carbide can have a few hundred different structures depending on the stacking sequence. So the two that are most important for us are alpha and beta. silicon carbide. So beta silicon carbide is cubic. It's stable up to 1950 degrees C, and then it transforms to alpha silicon carbide. Here are the C-4 ions, and here are your Si4 ions. So they're both in fourfold coordination, either way you look at it. So there's a stacking sequence here, A, B, C, and then it continues A, B, and C. So that's the stacking sequence for the beta silicon carbide. And then alpha silicon carbide is hexagonal. It's stable at temperatures higher than 1950 degrees C. So we'll talk about polymorphic phase transformations in a few minutes, but this goes through a phase transformation at 1950 degrees C. So here's your C-4 ions, the black small circles, and then your Si+4 ions are the large black circles, all in fourfold coordination. But now the stacking sequence is ABC, ACB, then ABC again. So depending how you stack these layers, you can have several hundred different forms of silicon carbide. And then the other useful refractory, non-oxide refractory material is silicon nitride, Si3 and 4. So you have the large Si4 ions in a close packed structure with the smaller N-3 ions in interstitial positions. So there's an alpha and a beta form of silicon nitride. Alpha silicon nitride is in the trigonal crystal structure, and it's stable up to 1550 degrees C. So the large black circles are the Si+4 ions, and then there's the N-3 ions, the small black circles. And then the other form of silicon nitride, beta silicon nitride, is hexagonal. It's stable above 1550 degrees C. Either silicon carbide or silicon nitride do not have a melting point. They just decompose at high temperatures. So again, the larger black circles are the Si+4 ions, and then the smaller circles are the N-3 ions. And then a mineral that's important in refractory materials in the fire clay bricks and in the higher alumina bricks are the clay minerals. So clays are hydrated aluminosilicates, and they're based on a combination of basically two layers, a silica layer and an alumina layer. So Si2O5N is the silica layer. You basically have SiO4 tetrahedra, and they're joined at the corners. That makes up one layer. And then the alumina layer, AlOH taken twice. That layer, you have alumina octahedra, and they're joined at edges. So this is what the silica layer looks like. SiO4 tetrahedra joined at the corners. So this is a silica layer, Si2O5. The open circles are oxygen. The small black circles are silicon. So each silicon is sitting in an oxygen tetrahedron. So here's 1, 2, 3, and here's your fourth oxygen. It can either be above or below the plane. And they're all joined at the corners by their oxygens. So that's the silica layer. And then the alumina layer, you have alumina octahedra joined at edges. So the black circle is alumina, the open circle is oxygen, the double ring circle is the hydroxyl OH. So you have an aluminum ion sitting in an octahedron composed of 2 oxygens and 4 hydroxyls. And then they're joined at the faces, sorry, the edges. So that's your aluminum layer, AlO, OH taken twice. So depending on how these layers are stacked, you have different clay minerals. So this stacking, 1 aluminum layer, 1 silica layer, is basically kaolinite, very common clay used for refractory materials. So here's your silica layer. The small open circle is Si, the larger open circles are oxygen, and then that's joined with the aluminum layer. These larger or intermediate, basically intermediate open circles are aluminum. All the shaded circles are OH groups. So you can see the silicon tetrahedrons, the aluminum octahedrons, and they're joined through these oxygens. So this is a clay structure, kaolinite, with 1 silica and 1 aluminum layer. This would be the side view of that structure. So there's 3 different classes of clay minerals. Again, the hydrous aluminosilicates, when you mix them with water, they become very plastic. So the first group here is the kaolinite group, and I just showed the kaolinite structure. It's Al2, Si2O5, OH4. Halosite is basically the same chemistry, except it's hydrated. It has two H2Os in the formula. So these are schematic diagrams. They're kind of like side views of the clay structures. This is kaolinite, and this is halosite. So the large circle is oxygen, the black circle is silicon, the crosshatch circle is aluminum, and the double ring circles are the OH groups. So you see your distinct silica layer and then your aluminum layer. So these layers just stack up. And then halosite is the same structure. You have your silica layer, your aluminum layer, but you have a water layer between these alumina silica layers. So that's the kaolinite group and 2 of the minerals in that group. There's a montmorillonite group, and now there's some substitutions into the structure. There's some magnesium substituted for aluminum in montmorillonite, plus there's additional H2O groups, and pyrophyllite is Al2, Si2O5, 2OH2. It's basically a different layer structure of kaolinite. So montmorillonite looks like this. You have your alumina layer, but now you have a silica layer above and below. So the open circles are oxygen, the double ring circles are OH groups. And this one circle that's half black and half white shows that there's some aluminum substitutions on the silica sites. And then this larger circle that's half cross-hatched and half white, right there, you have some magnesium substitutions on the aluminum site. So pyrophyllite is basically this triple layer structure without the substitutions. And montmorillonite has some aluminum ions on the silicon sites and some magnesium substitutions on the aluminum sites over here. Montmorillonite is hydrated, so there's a water layer in between. The third group is the illite group. So there's more substitutions here. This is mica. There's a potassium substitution on an aluminum site. There's an aluminum substitution on a silicon site. And then illite has magnesium and potassium substitutions on the aluminum sites and aluminum substitutions on the silicon sites, plus it's hydrated. So these structures get quite complex. And this is mica. So this is a silicon layer, an aluminum layer, and another silicon layer. Again, the oxygens are the open circles, the double ring circles are the hydroxyls. Silicon would be a solid circle, but it's substituted. So half of this circle is dark, half is white. That's an aluminum substitution on a silicon site. It's actually either, can be one or the other. Here's your aluminum and your aluminum layer. And now there's a potassium between the layers. So when you do some of these substitutions, you put an aluminum +3 on a silicon +4. In this case here, you have to balance, there's an extra negative charge, so you have to add another positive charge like potassium, a +1 charge, to balance the charge. So these ions that are between these layers are balancing the charge. So again, the clay minerals have two layers, the silica layer, SiO4 tetrahedra joined at the corners, the alumina layer, the alumina octahedra joined at the edges. And the different clay minerals are built up from different layer combinations. And then when you start substituting different cations, Al +3 and Fe +3 can substitute for Si +4 in the tetrahedral sites. Mg +2, Fe +2, and other ions can substitute for Al +3 in the octahedral sites. So you have your two basic layers. They can be put in different combinations, and then you have your different ions that can substitute on different sites. So substitution of cations is common in clays, and again, Al +3 and Fe +3 substitute for Si +4 at a tetrahedral site. Mg +2, Fe +2, and other +2 ions can substitute for Al in the octahedral sites. So when you make a substitution, you produce a negative charge in the structure. So if you put a +3 ion on a +4 site, it's going to have a negative one charge. Same thing here. If you put an Fe +2 ion on an Al +3 site, it'll have a -1 charge. So those are balanced by other ions that fit between the layers, like potassium +1, sodium +1, and even calcium +2. And there's another course in this sequence. It's probably the fourth course on processing. And the processing course talks about slip casting of clays to form refractory bodies. And these charges are very important when you start forming water-based suspensions of clays to form slips for slip casting. So that these charges help keep the material in suspension. But that's in another course on processing. So different crystal type, different crystal materials, different crystal types, they can have modifications of the same chemical compound. So different crystal structures of the same chemical compound. So these are polymorphs. So a lot of chemical compounds exist in more than one crystal structure. And when these compounds transform, as you heat them up from one crystal structure to another, that can be accompanied by large volume changes. So large changes in volume are going to disrupt ceramic or refractory materials, going to create stresses, going to create micro cracks, and can actually, in some cases, disintegrate the microstructures, depending on how large the volume changes are. So ZrO2 has a monoclinic to tetragonal transformation. Carbon is either in a diamond or a graphite structure. Silica has various transformations going from quartz to cristobalite to tridymite. So does kyanite. So these are some other raw materials in addition to the important ones for refractories: CrO2, carbon, SiO2. Boron nitride is also used in very small amounts in refractory materials and some of the composite materials. So which polymorph is stable over a particular temperature range is going to be a function of their free energies. So whichever polymorph has the lowest free energy, it's going to be the most stable. So here's an equation that describes the free energy G. So G is the free energy, is the energy that can do work. E is the internal energy, it's the energy stored in the chemical bonds. T is the temperature, and then S is the entropy. And you can think of entropy as the energy unavailable for doing work. So G equals E minus TS. And I put this on a plot here, energy versus temperature. And there's three different free energies, G1, G2, and G3, corresponding internal energies, E1, E2, and E3. And G3 is less than G2 is less than G1. E1 is less than E2 is less than E3. The entropies are going to follow the same trends as the internal energies E. So S1 is less than S2 is less than S3. So if we look at three different temperature regions here separated by these vertical dashed lines, the first temperature region here, the lowest temperature region, you can see G1 follows this path. G2 in this region is higher than G1, follows this path, and G3 in the same region is higher than G1, following this path. And here's the corresponding internal energies. So I highlighted in a darker color here the lowest free energy. So G1 in this temperature region has the lowest free energy. So whatever that crystal structure is, it has the lowest free energy and will be stable in that temperature region. And as we go up in temperature in the second region here, you can see that G2 is lower than either G1 and G3. So G2 will be stable in this region, whatever that crystal structure is. And then finally, in the highest temperature region, G3 is lower than both G1 and G2. So it will be the stable crystal structure. So I'm just showing whatever crystal structure has the lowest free energy of formation in the particular temperature range, that'll be the stable crystal structure. So it turns out there's two types of polymorphic phase transformations. There's a displacive transformation and a reconstructive transformation. So this displacive transformation is a change in secondary coordination by just distorting the structure. So you're just changing the bond angles. You're not breaking any bonds in the crystal structure. You're not changing the nearest neighbors, the number of nearest neighbors. You're just distorting the structure by changing the bond angle. So a displacive transformation is very rapid and it occurs at a specific temperature. So an example might be quartz. it goes through an alpha beta transformation at 573 degrees C. And specifically at that temperature, it changes crystal structures, and there's a volume change associated with that. The other polymorphic phase transformation is a reconstructive one. Now you change the secondary coordination by breaking bonds and reforming new structures. So this is a very slow transformation, and it takes place over a temperature range. So a reconstructive transformation example might be converting quartz to cristobalite. Sluggish, it occurs at a high temperature. You're breaking bonds and forming a entire new crystal structure. So when we go over the different refractory compositions, I'll point out which ones have displacive or reconstructive phase transformations. So this is a graphic example of a displacive and a reconstructive transformation. Here's an ordered two-dimensional planar type crystal structure. You have a small ion in the center of a cube of larger ions at the corners of the cube, and then the cubes are joined at their corners. So this is an ordered crystal structure. That's A. B or C are displacive transformations. You can see you have the same square structural units, the 4 ions at the corner, 1 in the center. They're still joined at the corners, but the bond angles between these structural units are different. So that's 2 examples of a displacive transformation. Again, it's a very rapid transformation at a specific temperature. And then the reconstructive transformation. Now you've broken bonds, you've reformed a completely different crystal structure. This is a slow transformation, usually taking place over a temperature range. So for displacive transformations, some characteristics. The low temperature distorted form is a lower energy structure than the high temperature form. The high temperature form has a lower specific gravity than the low temperature form. So it's a more open structure at high temperatures. The high temperature form has a higher heat capacity and entropy than the low temperature form. The high temperature form has a higher symmetry than the low temperature distorted form. And the important thing about this transformation is it's reversible. So if you have, let's say, ZrO2 going from monoclinic to tetragonal zirconia, every time you go through the transformation temperature, which is about 1100 degrees C, it's going to change crystal structures. And there's a volume change associated with that. It disrupts the structure, it forms microcracks in the microstructure, and it lowers the strength. So every time you go through these displacive transformations, you're going to have a change in crystal structure, whether you increase the temperature or decrease the temperature. A reconstructive transformation, some of the characteristics: interatomic bonds are broken and reformed. It's a slow or sluggish transformation because there's an activation energy barrier to overcome. A displacive transformation has no activation barrier. To make a reconstructive transformation take place, usually it's sluggish, it's a long time at a higher temperature, but you can enhance that transformation. You can create a liquid phase, which dissolves the unstable form, and then you precipitate the new stable form. This is exactly what you do when you add lime to silica to go from silica to cristobalite. You're dissolving the quartz and reprecipitating cristobalite. So you can create a liquid phase which enhances the reconstructive transformation rate. And the thing about reconstructive transformations, the high temperature form can be cool below the transformation temperature without reverting to the low temperature form. Whereas in a displacer transformation, the important thing here, the transformation is reversible. It's not necessarily reversible in a reconstructed transformation. So if we form cristobalite by adding a liquid phase through a lime mineralizer, the cristobalite, when you cool it down, will remain as cristobalite in a metastable form. So polymorphic crystalline changes are important. And as I mentioned, each time we go through a refractory composition, we'll go over them. And then the last thing here are crystal defects. There are different types of defects. There's point defects, line defects, planar defects, and volume defects. These are all present in ceramic and refractory materials. A point defect is zero-dimensional. A line defect is one-dimensional. A planar defect is two-dimensional. And then the volume defects are three-dimensional. So this is a zero-dimensional point defect known as a Schottky defect. So this is a crystal structure. Each size circle represents a different element. The large circle could be oxygen, and the small circle could be a positive cation. But in a Schottky defect, it's the simultaneous creation of both a cation and an anion vacancy. So you create the larger circle here would be your anion, smaller circle would be your cation. So now these are both removed, charges balanced in the crystal structure, but now you have two vacancies, an anion and a cation vacancy. So that's a Schottky defect. A Schottky defect is an intrinsic defect. It's thermally generated. So as you increase the temperature, you increase the concentration of Schottky defects. So the defect concentration increases with increasing temperature. So vacancies are forming in this stoichiometric ratio in order to preserve charge neutrality. So in this case, you removed one anion with a negative charge and one cation with a positive charge. So that maintains charge neutrality. So that could be MgO, one Mg plus two vacancy and one O minus two vacancy is created. Charge neutrality is maintained. TiO2, you have to create one Ti vacancy and now two oxygen vacancies to maintain charge neutrality. And in Al2O3, you have to create two Al vacancies and three O vacancies to maintain the charge neutrality. So that's the Schottky defect. There's another point defect known as a Frankel defect. So you're simply moving an ion from one position, from its normal position to an interstitial position. So here's a cation moving from its normal interstitial position, and it's in a new interstitial position. That's a Frankel type defect. Frankel defects are the same as Schottky defects. They're intrinsic, they're thermally generated. So as you increase the temperature, you increase the number of these Frankel interstitial defects. So you have a vacancy and an interstitial. They're basically linked together to form a defect pair. So this vacancy and this interstitial is a defect pair. They can form on either the cation or the anion sublattices. So it doesn't have to be a cation moving to an interstitial. It can be an anion moving to an interstitial site. And then you can also have simple vacancies. So here's a vacancy, basically a missing atom. So simple vacancies are not intrinsic, they're extrinsic. Simple vacancies are generated by adding a dopant. So the defect concentration is constant, and it's a function of the dopant level. So the defect concentration is constant with increasing temperature. So temperature has no effect on the vacancy concentration if it's an extrinsic defect. You can also have a simple interstitial. So here's an ion in an interstitial position. Here's another one. So that's another type of dopant, an interstitial dopant. These are also extrinsic defects. They're generated by adding dopants. They're not a function of temperature. So their concentration is constant depending on the dopant level. So temperature does not change these interstitial concentrations. The one-dimensional defects are dislocations. This is an edge dislocation. So this is a perfect crystal structure. And then when we have an edge dislocation, we have this extra line of atoms. So you can see that there's an extra line here. And then this vector B is known as the Berger's vector. It just closes the loop around the defect. So here's the loop around the perfect crystal, and then here's the loop when you have an edge dislocation, and here's the Berger's vector that will close that loop. And in an edge dislocation, the Berger's vector is perpendicular to this line dislocation, this extra line of atoms. And when the dislocation moves, this line moves across the crystal structure. That's how an edge dislocation moves. And then the other type of one-dimensional line defect is a screw dislocation. Here's your dislocation line. And the screw dislocation is basically a spiral stacking of the atoms. Here's your Berger's vector B. So this location moves around this dislocation line. And now B is parallel, the Berger's vector is parallel to the dislocation line, whereas in an edge dislocation, it was perpendicular. Dislocation movement is important in metals. It tends not to be very important in ceramics and refractory materials. The metal structures are much simpler than in ceramic or refractory microstructures, and ceramic and refractory microstructures or crystals, you have positive ions, negative ions. We saw binary compounds, ternary compounds. It just makes it difficult for a dislocation to move. But in some single crystals at high temperatures, you do have dislocation motion, and that adds to creep behavior in refractories at high temperatures. Planar defects are two-dimensional, and these would be grain boundaries between crystals in a polycrystalline material. So there's two types of grain boundaries, a homophase and a heterophase. So in this first one here, homophase, you have crystals of the same composition with different orientations at the boundary. So you have a polycrystalline material that's very pure. At the grain boundaries, you have two crystals in contact. You have a distorted structure at the grain boundary. That's a homophase grain boundary. In a heterophase grain boundary, you have a compositional difference. So impurities tend to segregate at grain boundaries. In refractory materials, so you have a lot of silicate amorphous type phases at the grain boundaries. So you have a silicate liquid at a high temperature, it cools to form amorphous type, glassy type material at the grain boundaries. So that's a heterophase grain boundary. So basically, the homophase has no impurities, just a disordered crystal structure at the grain boundaries. Hetero phase has impurities that are segregated at the grain boundaries. These amorphous phases control a lot of the high temperature properties like strength and creep resistance. So in this hetero phase grain boundary, you have a change in composition at the boundary. So if you have slow transport rate of atoms across the boundaries, slow diffusion rates of the atoms, you'll have an increase in resistance to creep and oxidation at high temperatures. If diffusion is fast across these grain boundaries, a high transport rate, that increases the thinning rate or densification rate. Also at high temperatures, it's also going to increase the creep and oxidation rates. And covalent materials are harder to sinter. There's strong bonding, but you usually have to add an impurity at the grain boundaries to get these to sinter. So you have to add a dopant to enhance the sintering rate of materials like silicon carbide and silicon nitride, and you want a high transport rate to enhance the sintering. And then volume defects, I think this is the last slide. These are three-dimensional defects. So you can think of a planar defect at a grain boundary. It's a thin grain boundary, it's two-dimensional. But if you have a substantial amount of material at the grain boundaries, it'll be rather thick. So you may have a thick silicate liquid that cools to an amorphous phase or a glass at the grain boundaries. So if you have an excessive amount of grain boundary phases, it becomes three-dimensional. Porosity is a volume defect between crystals. When we talk about microstructures, we'll talk about the effect of porosity. Porosity improves thermal insulation. It decreases strength. It improves thermal shock resistance. So porosity can have various effects on the properties of the material. So it's a three-dimensional defect. And you can also have secondary or exaggerated grain growth. This is the case where a crystal, a single crystal, or more than multiple crystals in a polycrystalline material grow to a very large size. It's called exaggerated grain growth. So you'll have a very large crystal in a polycrystalline structure, and that crystal will affect properties such as strength. A large crystal would lower the strength, but it would improve the creep resistance. So these are different types of three-dimensional defects. So we've covered the different crystal structures, polymorphs, and crystal defects. So the last thing that we have to discuss next Monday are glasses, because there's a lot of silicate liquids that are present in most refractory materials. And once we cover that, we have a couple lectures on phase diagrams, and then we'll go on to all the different refractory compositions. So again, thanks for attending, and have a good weekend. I'll see you on Monday.